Welcome to Read Along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 6.3.2. Okay, so in the last subsection, we talked about um, a certain type of merge that we'd like to do with grouping vertices together. When we're thinking about the vertices themselves as being like standard basis elements or vectors, if you will, in a module, in a free module generated by these guys. So just taking tuples with the multiples of these vertices as being the entries in the tuples. And we're now going to move to vector spaces and think of Z as now as Q. So our coefficients can be rational numbers or fractions. Okay, so what we were doing is we were saying, okay, let's merge V1 with V2 because there's an edge between those two guys. V1 with V3 because they have an edge between them. V5 with V4 because there's an edge between them, and V5 with V5 because it has an edge with it. Well, that's just, doesn't do anything new. Okay, so let's just remind ourselves what that graph looked like. This was what the graph looked like. So every time there's an edge, right, we're merging those two. Now, it's equivalent to say if we merge 1 and 3 together, that's like saying you merge 3 minus 1 with 0. It's equivalent, especially if we're assuming that the merge preserves addition. And so we could say, okay, this is what we're doing. We're going to have a merge that preserves the vector space structure. So that's equivalent for taking the initial domain Q5 and then chunking it up by the cosets of the cosets of this subgroup of Q5, the one that's generated by what we want to throw into 0 or to be included with 0 in the chunk of 0. So the cosets of this will yield with Q5, that'll yield a new vector space. It's called the quotient vector space. So which is isomorphic or the same as the image or the range of this merge. Okay. So now in this last case, notice that when we chunk things up, let's look back at our picture here. These guys will come together and these guys will come together. So this will be like one mega vertex and this is another mega vertex. And then the vector space will really be like taking something times something times this vector, or which is now one mega thing that's been merged, plus something times this one. So like the span of these two megavectors, in which each megavector is like a connected component in that case. So hence we can quite literally, in this case, think, well, it's just the span of those two guys. And the quotient, the quotient's really just that. Well, and that's the smallest span we can get, which means that's the dimension. The dimension of the space of this quotient space is 2. So it's kind of like we're taking a vector space and we're taking a quotient of it with a sub-vector space. See 0 bar here is always when we're merging and we're preserving structure, that actually always ends up being a vector space itself, the subspace of our original one right here. And when you quotient, just like these are groups as well, use the quotient as groups or as vector spaces. But if you quotient them as vector spaces, you get a vector space, but the vectors are like chunks now. Like each chunk is like a vector and it behaves the same way. So, and each chunk represents a connected component. All right, so as we move, so we have a merge from Q5 to this chunking. And so it's a surjective merge, and the resulting range has a dimension. That dimension is precisely the number of connected components. And this basic idea is pretty much what's discussed down here. Um, a couple notes. Notice what this is right here. This is like an incidence matrix because you notice what zero bar is. It's the span of these guys right here. Um, and notice what this is. This is like v2 minus v1. This is like having an edge between these two guys, but making one edge have like a negative incidence, the other one, or one vertex that's connected to that edge have a negative incidence, and another vertex connected with that same edge is having a positive incidence. It's kind of, and if we list out these as vectors, notice it looks like an incidence matrix. So collecting the edge information in an incidence matrix is the same thing as collecting edge information in a span to make a subspace of something that you want to quotient out by, and then you want to look at what the dimension of the image of that quotient is, or what the dimension of the quotient basically is, and that dimension will be the number of connected components. How could we read that off, though, just by looking at the incidence matrix itself? Remember, the incidence matrix gives us so the incidence matrix itself gives us what we're quotienting out by, what we want to make equal to 0. So we can find the dimension of what we're making equal to 0 by finding a Smith normal form. So that dimension would be, notice, 3. So these guys right here, let's just think about, like these vectors together. Like how many do we need to create the span of what they are? Well, you need all 3 of them. Dimension is 3. Smith normal form will tell us that. Okay, so the Smith normal form of the incidence matrix tells us the size of the 0 part, or what we're modding out by. The size of what we're modding out by dimension-wise. This has dimension 3. That's what we're modding out by. In some sense, you can kind of roughly think of it this way, and this is just the way I'll describe it here. We have, so what we mod out by has dimension 3, but remember that the domain had dimension 5. But the kernel of this map, or the kernel of the quotient map. So this is not the quotient map. This is just an analysis of what we're modding out by. That's really what we're looking at. So but we have a map that goes from domain, which has dimension 5, and it goes to Q goes to a quotient, and we're quotienting out by something. I'll just call it 0 bar. All right. So we're quotienting out Q5 quotient out. So, and that has the dimension of this is precisely the dimension of the range of this map. Dimension of the range. And what we just found right here is like the dimension of the kernel. So let's just make another map here, call it F, okay? So actually this F differs from that one in the text, so maybe I'll rewrite it. Maybe I'll call it, I'll just call it M for map, okay? So, all right. So let's suppose we have M, and M is it's a map between vector spaces. It has a matrix. Its Smith normal form, when you read it, will have some form. It will have, since this has a kernel, the dimension of the kernel we know will be 3. So we're going to have 3. We're going to have, let's see, in the output. Okay, the output, we know in this particular case the output has dimension 2. Okay, so and the input has dimension 5. So the matrix will be have 2 rows and 5 columns, so it'll be a 2 by 5. And since the kernel of this, what we're modding out by, has dimension 3, we'll have 3 columns with zeros. And then the rest won't be zeros, so it'll just be the normal thing. like this. And this actually tells us the dimension of the range. Remember what the dimension of the range is. It's the dimension of this quotient vector space that we're looking at, which and the dimension of that will tell us the number of connected components. So right here, well, notice, so notice what 2 and 3 do. They add together to get 5. So you take the original dimension 5, and you can think of it this way. The number of, so we see here, the dimension of the range is actually the number of connected components is equal to number of connected components. And then you add the dimension of the range of the Smith normal form. Dimension of the incidence matrix. Okay, dimension of range of the incidence matrix thought of as a map itself. So dimension of range of the, I'll just point an arrow to it, of the incidence matrix. So dimension 5. So how do you compute the number of connected components in general? You take the original dimension, which, remember what the original dimension is? It's just the number of vertices we were starting with. So number of vertices. So this actually gives us something quite good. Number of vertices is equal to the number of connected components plus the dimension of the range of the Smith normal form. So just the number of ones you see in the Smith normal form. Okay. So if we solve for number of connected components, number of connected components is equal to number of vertices minus, so number of vertices minus the number of ones in the Smith normal form of the incidence, which is the dimension of the range. Okay, number of ones in Smith normal form of incidence matrix. Now, notice that the original matrix did not have orientation, but our incidence matrix did, meaning direction on the edges. So actually, this works. We just have to turn our graph into a digraph, and it doesn't even matter how we do it. We just have to have every edge directed so that we actually have two things, like the subtraction of the two things going to 0. So that actually kind of naturally in an incidence matrix creates a direction. So that's why we call it oriented. It has direction. So you have any graph at all, you can make an oriented incidence matrix for it by just having a 1 and a -1. It doesn't matter which one you put as 1 or -1. You just have to have it in there somewhere. And then the Smith normal form of that, you count the number of ones in that, you subtract it from the number of vertices you start with, and that's actually equal to the number of connected components. Kind of neat. So what do? Just take your incidence matrix, find Smith normal form, see how many ones you have, and subtract that from the number of vertices, and you got the number of connected components. It's kind of a neat little calculation. Thanks for watching.